Okay, got a couple more formulas up on the board here. These are formulas that tend to show up when we have resonant forcing, because we've got T times sine omega t and T times cosine of omega t. So that gives us formulas 4 and 9. Now, you are sort of asked to derive these formulas in question 35 of your homework. And there's a big note in the homework to sort of caution you about this, because I think the book is a little bit irresponsible here. Okay, 35 part A asks you to show that the Laplace transform of t times f of t, so in these cases my f of t would just be cosine omega t or sine omega t, is actually the opposite of the derivative with respect to s of the Laplace transform of f of t. Now, that is true. I think it's irresponsible of the book to ask you to prove that, because we don't have the tools to prove that at this point. So I have only assigned 35b, which is asking you to take this as given and apply it to prove this formula for sine omega t. So you would basically take the Laplace transform for sine, which is a function of s, take the derivative with respect to s, and you get this. And you could do something similar for cosine. Take the formula for the Laplace transform for cosine. It's a function of s. Take the derivative with respect to s. And I'm sorry, you don't get this. You get the opposite of this, because there's that negative sign. But I did want to just address why you don't have the tools to do this. Okay? Because essentially, this would have me be taking the opposite of the derivative with respect to s of the integral from 0 to infinity of f of t times e to the negative st dt. Now, I can see that if I just pulled that d by ds in and put it right here and took the derivative of this, that's going to give me e to the negative st times negative t. It's going to give me that factor of t that I'm looking for. But the question is, can I pull that derivative inside of the integral? Now, the answer in this case is yes, but only because you check that certain conditions are satisfied, and you don't know what those conditions are or how to check them, okay, because we haven't covered that. In general in math, it's a big deal when you interchange two processes that are defined in terms of infinite limits and things like that. So it does work, but I don't want you to just blandly assume that you can interchange the order of integration and differentiation in every case, because you can't. And in upper division and graduate level math classes, you start to look at what conditions need to be satisfied in order for me to interchange the order of those things. So the book should not have asked you to prove this. The book should have said, this is true. Now use it to find the formulas for the Laplace transform of t sine omega t and t cosine omega t. If I were to ask you to derive these formulas on an exam, I would give you this and tell you that it was true, so that all you'd be doing is taking a derivative. Okay. That would actually make it a really easy question, so you can hope I do that and be pretty sure I probably won't. Okay. All right, so I did want to just address that issue. As I said, there's a big note in the homework about that. It's actually mislabeled initially as question 33, but it's question 35. But the note certainly applies to it. Okay, what I want to do is just practice using this in a nice simple example. Let's suppose I have y double prime plus 4y equals cosine of 2t, where y of 0 is 0 and y prime of 0 is also 0. So this is similar to an example that you have in your textbook of a fairly nice initial value problem. Definitely one for which we don't need Laplace transforms, because I don't have any discontinuities here. So I could just solve this the way we've solved these before in chapter 4, but I'm going to go ahead and use Laplace transforms. Okay. So I'm going to do a little bit of side work for the Laplace transform of y double prime. Remember, that's the Laplace transform of the derivative of y prime. And that gives me s times the Laplace transform of y prime minus y prime at 0. That's formula 11. Okay. Y prime of 0 is just 0, so that piece drops out. So using formula 11 again, this is going to be s times the Laplace transform of y minus y of 0. But since y of 0 is 0, that piece drops out. So I'm just getting s squared times the Laplace transform of y. Plus, this will be 4 times the Laplace transform of y. And now we've got our cosine of omega t. That Laplace transform is going to be s over s squared plus 4. Let me see what formula that is. That is formula 7, where 2 is my omega, and so this is just a 2 squared here on the bottom. Okay, so I can factor out the Laplace transform of y, and it's being multiplied by s squared plus 4, and that's equal to s over s squared plus 4. So the Laplace transform of y is equal to s over s squared plus 4 squared. So when I see this irreducible quadratic squared, that sort of makes me look to see if I've got something like this. Looks like it's going to be easier to match this one because I have just an s on top, and it looks like I want to end up with a multiple of s. I want to have a 2 and an omega. Okay. So we said our omega here was actually just 2. That was the angular frequency of this forced response. So 2 times omega is 2 times 2 is 4. So I'd like to have a 4 here. So I'll multiply by 1 in the form of 4/4. And that way I've got 1/4 4s over s squared plus 4 quantity squared. And that now is a perfect match for this with omega equaling 2. So if I take y, I'm going to get 1/4 the inverse Laplace transform of 4s over s squared plus 4, and that's going to be 1/4 t sine of 2t. So that one wasn't so bad. Laplace transforms can be very tedious. Certainly the last example that we did, there was a lot of tedious calculation to be done, but sometimes they're pretty straightforward and fairly simple to work with. Okay. So just wanted to show you that. We'll move on to another discontinuous function in the next section.